This is Elemental Physics from Physics Geeks. This is a series of episodes dedicated to the understanding of mathematical concepts behind physics. The first episode of this series will be on vectors. We as individuals who learn physics come across vectors in many physics problems, from walking, driving, to sending rockets. Vectors help us solve problems involving forces, velocities, accelerations, and so on. As you may already know, the textbook definition of a vector is an element of a vector space with a magnitude and a direction. But what does this mean? First, what is a vector space? It is a theoretical space where a field of numbers, also known as scalars and vectors, exist. It can perform two operations, which are vector addition and scalar multiplication. Any vector can be represented by a line segment. While the direction of it provides the direction of the vector, its size or length corresponds to the magnitude of the vector. Before discussing the vector addition and scalar multiplication, we'll learn how to make an equal vector to a given vector. Suppose we have a vector OA. If we name this A, then any line segment with equal magnitude to that of OA and parallel to it will also represent A anywhere within the vector space. Vector addition is when two vectors of a vector space are taken and added together to create a third vector. In scalar multiplication, a scalar is taken from the number field, which then is multiplied by a vector to create a third vector. Now, with this knowledge, we'll start vector addition. Vector addition is of two types. Number one, when two vectors are collinear or parallel. Number two, when two vectors are at an angle to each other. If we consider the first case, when the two vectors are collinear or parallel. Now this is similar to normal addition. If the two vectors A and B are to the same direction, then A plus B means the numeric addition itself. Here vector A plus B is parallel to vectors A and B, and the modulus of A plus B is equal to the modulus of A plus the modulus of B. When two vectors are opposite in direction, we take the mere subtraction. Easy. Then the resultant vector A minus B means the numeric subtraction itself. Similarly, vector A minus B is parallel to vectors A and B, and modulus of A minus B is equal to the modulus of A minus the modulus of B. The theory is different when two vectors are at an angle to each other, and if we call this angle theta. If we consider mere numeric addition, in this case, we are wrong. When dealing with these type of problems, we use a theorem called the parallelogram law of vector addition. The parallelogram law states that when two vectors A and B are spreading out from a point, and if we are to take its resultant, by completing the parallelogram with vectors A and B as its adjacent sides, then the diagonal of the constructed parallelogram through the intersection of A and B will give the resultant. Its length will give us the magnitude, while the angle it makes with either A or B will give its direction. It's relative. You can get the direction in any way you want, with the horizontal, vertical, or with respect to a given vector. To clarify this, we will look into the following problem. Consider two vectors P and Q spreading out from a point which are at an angle theta to each other. Prove that the resultant R is given by R squared is equal to P squared plus Q squared plus 2PQ cos theta, where theta is in between pi by 2 and 0. And that the direction is given by tan alpha, where tan alpha is equal to P sin theta over Q plus P cos theta. Okay, now if we try to solve this, P and Q are said to be spreading out from a point. So let's sketch it like this. Now our goal should be to combine this problem with the parallelogram law. So what should we do? We should create an equal vector to either P or Q. How do we do it? If I create an equal vector to P, I will draw it at the point at which vector Q ends so that P and Q are subsequent. Now what can you do? Now you can complete the parallelogram. What will be our next step? We should draw the diagonal. Name the magnitude of the diagonal as R because now we know that the diagonal gives the resultant of P and Q in the direction and magnitude. Now the physics is over. What remains is the math. Name the constructed parallelogram as OABC as follows and drop a perpendicular to OA produced from B and name its foot as D. Now what do you see? Yes, a right angle triangle. It's this triangle ABD. By equal vectors, what do we know? We know that vector AB is equal to vector OC or vector P. By trigonometric resolution, we get that AD is equal to P cos theta and that BD is equal to P sin theta. Now we see another right angle triangle. What is it? Yes, it is OBD triangle. What is the theorem which hits our mind when we see a right angle triangle? Obviously, it is the Pythagorean theorem. By the Pythagorean theorem, we get that OB squared is equal to OD squared plus BD squared. Now what should we do? Yes, substitute the above derived value in this equation. Now we get that R squared is equal to Q plus P cos theta squared plus P sin theta squared. Now it's just simplification. What do you see? Simplify the bracket. By binomial expansion, we get Q squared plus P cos theta squared plus 2PQ cos theta plus P sin theta squared. By the trigonometric identity, sin square theta plus cos squared theta is equal to 1. Take P squared plus Q squared out from a bracket and show how sin squared theta plus cos squared theta is a common factor, and that is equal to 1. Now we have the needed answer. And the next part is pretty easy. We are asked to find the direction. Get an expression for tan alpha. It would be tan alpha is equal to P sin theta over Q plus P cos theta. If you look at the diagram, you'll understand how this expression is obtained. Now at the end, if I remind you what we learned up to now in this episode, we defined a vector. We learned how to denote a vector geometrically. We learned how to construct equal vectors. Then we did vector addition under two subsections where the two vectors were collinear and where the two vectors are non-parallel. That is where we learned the most important part of today's episode, the parallelogram law. So we hope to discuss vectors up to a larger extent in future episodes, starting from the lambda mu theorem in the next episode. Until then, goodbye.